Okay. I don't want to thank the organizers, but I'd like to thank the participants for making this a great meeting. I have to confess I engaged in a little bit of abuse of power, maybe inspired by our national leaders or something, in asking Ragnar to give a summary of finite element exterior calculus in an hour, which is an impossible job, but is a great setup for me. And I'm going to just start by hitting a few highlights of that, which is, I think, sort of the takeaway messages, now that you've had the high survey. So here's my outline. I'll do these highlights of Feec, and then I'm going to talk about two ways that these Feec, finite element exterior calculus, might apply to GR. I just looked back. I think the first place where Feec was sort of brought up, and it didn't even yet have the name, was I gave a plenary lecture at the International Congress of Mathematicians, and you had to write a paper that went along with that. And I explained these ideas and that they were having big success on things like the elasticity equations. And I said, and it seems likely they will have a big role to play in difficult PDEs that have a big geometric content, like numerical relativity. So I'm a little burned in that because they haven't had such a big effect, and that explains the question mark on my slides. But let's see what we think about it after you've seen it. And I'm going to talk about these two things. They were each subject of a thesis of a student of mine. I've been working a lot on Feec and not very much on numerical relativity for the last 10 years. But I did have two students who wrote theses on these, and I'll name them when the time comes. As far as Feec goes, I have a favorite reference in those list of references, which is this. It's thin. I think it's quite accessible. It has pictures. It's cheap. And you can download it from SciAm if your university has a license from it. So that's a place where you can go to get some more. Okay, so the first thing, I mean, as you saw, we keep talking about complexes. So what's a complex? A complex is just a sequence of spaces. All sorts of different spaces can be combined in complexes, and a sequence of operators between them, D0, D1, D2. And the only property it has to have is that if you do two Ds in a row, you go from D0 to W2, or from W1 to W3, via two Ds you get 0. So the spaces have to have a 0, like for us they'll be Hilbert spaces, vector spaces. We won't be talking about Hilbert spaces with bounded operators. It's more general than that. And the thing you should have in mind is something like, suppose you have L2 and L2 vector fields, and you want to have the gradient as a map from scalar functions to vector functions. Well, of course, the gradient is not bounded on all of L2. It doesn't map. Everything in L2 doesn't have a gradient. So you take a domain, which is a part of L2, exactly those things whose gradient is in the next L2. So we'll put a domain there, V0, which is smaller. So each of these also has a space in it. That's called the Hilbert complex then. And so you have to give a bunch of Hilbert spaces, a bunch of differential operators with d squared is 0, and say what their domains are. That's a Hilbert complex. And actually, for our purposes, we don't need the whole complex. We only need 3 spaces. So I'll minimize. You give 3 spaces, W0, W1, W2, 2 Ds, D0 and D1. Their domains are the V0, V1, which is a dense subspace of the corresponding W0 and W1, with this one property that D1 composed with D0 is 0, which is usually abbreviated to D squared is 0. Once you have that structure, okay, and then we give one more property to this called, to say it's a closed Hilbert complex, means that the range of the D operators are closed in the next space. And we'll always assume that's the case. It is in all the cases we need. The dual complex, whenever you have a densely defined closed operator, then you have a dual operator. It has its own domain. It goes back in the other direction from the second Hilbert space to the first, and it has its own domain, V1 star, so we get a dual complex. And then if you start in the middle space, W1, you can take the D operator to the right and then the D star 2 operator back to the left, or you could take the D1 star operator to the left and then the D0 operator back to the right. So you get DD star plus D star D, if you add them together, is a map from W1 to W1. Yes? It has a domain. It's So the, so no, but that doesn't matter. So let's take that case. So let's take this case here. The by the way, thanks for questions and please keep it up. So H1, the Sobolev space of things in L2, whose gradient is in L2, is the domain here. What's the adjoint? Well, the adjoint of grad, you won't be surprised, is minus div. And which things is it's defined on? H div. Those thing L2 vector fields whose divergence is in L2. So that's the, this is the dual minus div with domain H div is the dual of grad with domain H1.
So, I mean, the notation suggests that we should be thinking about exterior derivatives and Hodge dual.
So without a doubt, the key, the canonical example that motivated the definition was the de Rham complex, which would be something like L2, then the gradient. Can you see that, or do I need to write bigger? Let me do it here. So we take L2, and we take grad, and its domain is H1, and we take L2 vectors, and we take, the next one would be curl, and its domain is everything whose curl is in L2. And of course, this maps into this one because the curl of a gradient is 0. So it's in H curl, and what's more, dd is 0. And this gets us to vector fields again. By the way, this is only in R3 if I'm using the notation curl. And in fact, you can continue here. This goes into the divergence with the domain H div, and divergence of curl is 0, and that would get you into L2. And that's where it ends. You can put a 0 here if you want. Put a 0 here. And these, of course, is the concrete calculus realization of differential forms. In a more differential form language, I would put L2 differential 0 forms here. And I'd have the D operator, D0, and its domain is called H lambda 0, which is the name of things, L2 differential forms, whose D is also L2. So this would be L2 1 forms. And then we would have D H lambda 1, L2 2 forms, and this could go L2 2 forms, and this could go all the way in n dimensions to L2 n forms and 0. That is the de Rham complex. That's the Hilbert version, the L2 version of the de Rham complex. There's also a smooth version and so forth. And that's the concrete realization of it in 3 dimensions. They have names for the D's in 3 dimensions. We don't have names for them in 4 and 5 dimensions. And this is the abstraction of that. Just make them Hilbert spaces. They don't even have to be differential operators and functions. Okay? Any other questions? Okay. So whenever we have one of these complexes, we have a dual complex, and we can form a Hodge Laplacian. So really, this is the thing we care about. That's a PDE to solve. If I can convince you that we care about that particular PDE, for any particular realization choice of the W's and the D's, I get an operator, which is in practice a PDE, the Hodge Laplacian dd star plus d star d. And we use, for the reasons that Ragnar pointed out, we use a weak formulation where we introduce a new variable. So this is the weak formulation. Find a sigma in the domain of the first d and a u in the domain of the second d, such that the W inner product of sigma tau, the W0 inner product of sigma tau, minus the W1 inner product of u and d tau is equal to 0 for all tau in the domain of d, so forth. What does this say? Well, this d is the adjoint of d star, so if I put it on the u, this would say sigma minus d star u is orthogonal to all taus. This is a way to say weakly sigma is d star u. But I get to say it without having to get a function in the domain of d star. It comes out in a weak sense. And it might imply some boundary conditions as well. And this one says weakly that d sigma plus d star du is equal to f. And since sigma is d star u, that's d star u plus d star du is equal to f. So this is the Hodge Laplacian. Okay. And now you can analyze whether this is a well-posed problem in this degree of generality, this sort of super generality covers a zillion things, it's always well posed. Well, not true. It's possible that you could have a function u that's in the null space of both d star and the null space of d. So, of course, d star plus d star d of it is 0. So there's a kernel to this space. And correspondingly, there are some f's that are not in the range of the Hodge Laplacian. And that's measured by the cohomology, which is what complexes are all about. It measures the difference between the null space of D1 and the range of D0 inside it. In fact, the so-called harmonic forms that Ragnar brought up, they're exactly the things in the null space of D1, but orthogonal to the range of D0. For instance, for this problem here, there are functions that are in the null space of curl, but orthogonal to the range of the gradient. Exactly the dimension of that space of functions is exactly how many holes you have in the domain. That's why there was a 0 eigenvalue when there was a hole in the domain. Okay, that's crucial, and this is a big part of the motivation why something like this is necessary. So to solve a problem like this, you can't solve it quite in this form. You have to take into account the harmonic forms. You have to put one compatibility condition on the data for every harmonic form, and you have to put one side condition on the solution to make it unique. Just like in Einstein, there's a gauge, but it's only finite dimensional. Now, if your numerical method doesn't capture that, you're in big trouble, because then you can't even tell your numerical method what the side conditions it has to satisfy is. Maybe you don't have enough harmonic forms on the discrete level to even impose your side conditions. Well, it can't get the right solution if you don't tell it the whole problem. Okay, so what I'll be trying to do is squeeze a lot of problems into the form of the abstract Hodge Laplacian for some complex, because those are ones that we can obey this theory. Now here's another one, because whenever I talk to relativity people, say, oh God, these elliptic problems, where do we solve hyperbolic problems? So let's go to the Hodge wave equation, whose so-called spatial part, the part that's not two time derivatives, is the Hodge Laplacian. So it's just like the wave equation. So I called the variable capital U double dot plus dd star plus d star du is 0, and you have initial conditions. Okay, the way you solve this is you introduce sigma's d star capital U, just like we did for the Hodge Laplacian. I also am going to give a name to d capital U, which we didn't need to do for the Hodge Laplacian, call it rho. And I'm going to introduce the velocity, U is U dot, capital U dot. And then if you write it out, it satisfies this first order evolution system. Sigma dot is minus d star u. Well, that's just what happens if you dot this equation. You get sigma dot equals d star of little u. And u dot plus d sigma plus d, well, rho dot is minus d u, which is what happens if you dot the second equation here. And then u dot is d sigma plus d star rho. So I've gotten the equation in there. And you notice this nice skew symmetric operator here. Even in this vast generality, this is skew symmetric operator. That's saying that if you did this for a differential problem, where the d's were differential operators, you'd have a symmetric hyperbolic system, and it would behave nicely. So this is always a nice problem. Here's the weak formulation of it. It's pretty much straightforward from the strong formulation. And it looks very much like the Hodge Laplacian, but now there are these dotted terms here. And then there's a theorem which says, we don't care about the exact spaces. Of course, they're important for mathematical correctness. But if you take any initial data, then there is a unique solution to this system. And how do you prove that? Well, there's something called a Hille-Yosida theorem, which says that that an evolution equation is well posed if the corresponding spatial operator has certain properties, maximal monotone, and those properties are exactly what we can prove from the Hilbert complex sort of theory. So if you can turn a problem into an abstract Hodge wave equation, it's going to be well posed. Okay, here's an example which hopefully a lot of people will care about, Maxwell's equations. I could have done the full business. Here I took a zero imposed current, but it wouldn't be necessary. So we have the Ampere's law and Faraday's law and Gauss's law. D dot is curl H, B dot is minus curl E, the divergence conditions, and the constitutive relations, I'm assuming are linear here, but the epsilon and mu do not have to be scalar, they do not have to be constant. And I claim this is the Hodge wave equation if you look at it the right way. Even though it has constraints, even though it looks quite different, it has 4 variables and so forth. So here's how I'm going to turn in the Hodge wave equation. This is completely different than any form of Maxwell that I've heard about in this meeting. There's no potentials. We're not introducing the vector potential or anything here. I have to choose 3 Hilbert spaces, right? And 2 Ds. That's what I have to do. I told you what a Hilbert complex is. So I need to tell you what W0, W1, and W2 is and what the Ds are. So they're all L2. The first one is L2 scalars, the second L2 vectors, the third L2 vectors, but not quite L2, L2 with a weight. So it's not the L2 inner product, but the weighted inner product, weighted by, I can never remember which is permeativity and permeability, but the first one's weighted by epsilon and the other one by the inverse of mu. And then the operators are just grad and curl with domains H1 and H curl, just like the de Rham complex. To get the right sign conventions, you have to put a minus in the curl, but that's not important. Then you write out the weak form of the Hodge-Laplacian, exactly just do what this tells you to do. Just write that down for those spaces. That means the inner product, whenever it's using the space W1, will have an epsilon, and whenever it's using the space W2, will have a mu inverse. So this is the weak form. And that still doesn't look anything like Maxwell, but I claim it is Maxwell. So there's this funny term sigma here, which doesn't appear among the variables in Maxwell. But what's going to happen is sigma is going to be 0, and this equation will be the equation div d, because epsilon e is d, div d is equal to 0 imposed weakly. So here's the theorem. Take your initial data. Well, if you take initial data for Maxwell, of course, it has to satisfy some compatibility conditions. The B and D have to be divergence free, or else you can't satisfy the divergence constraints. So take initial data for sigma E and B. You have to have the constitutive relation D equals epsilon E and mu H equals mu inverse B satisfied in the initial data, and assume that the initial data satisfies vanishing of divergence for D and B, and that sigma is 0, because sigma is supposed to turn out to be 0 for all time. So assume your initial data satisfies those compatibility conditions. This is the Hodge wave equation, which always has a unique solution, and the theorem says that unique solution will have sigma identically 0, and E, B, D, and H will satisfy all the Maxwell's equations, including the constraints. Luis? All over the place. How do you know when you write down something like this that it has a unique solution? Or if you would go back to here, how do you know that this has a unique solution? So you use the complex in that, you use the fact that you have the adjoints and so forth. Right? I mean, you just write down a PD, it's almost never well posed. What makes it well posed? A certain structure. So, well, one thing I'm going to do among the many things that are done in proving this would be to take tau is equal to sigma, E is equal to F, and C is equal to B, and add these up, and then the second term of the first equation will cancel out the first term of the second equation, and I'll get a L2 stability, an energy stability. That's just one of the things that exploits the structure of these equations. Well, would you have put sigma in there without thinking of the complex? Maybe, because you're a smart guy, but it's... Anyway, so the point is that you can take an important problem and you can fiddle around with it a little bit and realize that it's just the Hodge wave equation. And actually, the way I think about this a little bit, so it's obvious that Maxwell is basically E double dot is curl curl E, minus curl curl E. But that's not a very nice equation, weakly hyperbolic, blah, blah, blah. You can add grads and divs in the right way to make that a nice equation, and if you do it right, it doesn't change anything because those extra terms turn out to be 0. This is doing that. And of course, you had thought of that before, but it's not the first thing that you think of. Okay, So that's one thing. You write down a short complex and you can get a Hodge-Laplacian, a Hodge wave equation, etc. Then another highlight of the finite element exterior calculus is how do you discretize these? Well, in finite elements, you have a weak form you discretize by what's called Galerkin's method. You take subspaces for the trial functions and the test functions. So we're going to discretize by Galerkin method, meaning that we're not going to take functions into H1, H curl, and L2, but into some finite dimensional subspaces of those, which of course will be finite element spaces. Okay, and does that always work? Can you pick any finite element spaces you want and do this? No, it does not. It absolutely does not, and that's what the examples that Ragnar showed you in the beginning are. You do that, it seems reasonable, and you get garbage. And even worse, you get reasonable looking garbage. So what do you do about that? Well, you have to choose spaces that have some properties, and one of the big take-home messages of finite element exterior calculus, two properties beyond that they're rich subspaces. One is they have to form a subcomplex themselves. That is, the D has to map this space into this space, and this space into this space. The H's mean the subspaces. So you get a subcomplex, and then the one that Ragnar emphasized quite a lot, you need projection operators going down that commute with the D's. That's pretty hard to get. Pi D is D pi. And what's more, they have to be bounded, and that makes it even harder. And that's a way to take properties. That's a way to say the discrete problem has similar properties to the true problem. For example, when these things hold, it's a theorem that the cohomology of the discrete complex, the harmonic forms, has the same dimension as the true complex. Not only same dimension, but it's close in norm in some sense. So your side conditions on the discrete level are good matches for your side conditions on the true level, and your compatibility conditions. So I would regard this as a prime example of the philosophy of structure preservation. Okay, then comes the next part. How do you generate subspaces that satisfy those somewhat hard to meet conditions? And here I can't say, well, finite element exterior calculus gives you a simple recipe. Every complex needs its own consideration, and there are complexes which we don't have good finite elements for yet. How do you go about this? Well, this is something about all finite elements. Finite elements, as I guess Nora emphasized, you specify three things to specify a finite element space. One is the element shape, typically simplices, cubes, maybe slightly more complicated things. Then on each element, each simplex, each tetrahedron, each triangle, each cube, whatever, you specify a finite dimensional space of functions, almost always polynomials, called the shape functions. And then your finite elements are piecewise in that space, but pasted together with a certain degree of continuity. And that third thing is specified by saying what the degrees of freedom are, and associating those degrees of freedom to faces of different dimensions, vertices, edges, triangles, and so forth. You have to give the same number of degrees of freedom as the dimension of the shape function space. That has to be invertible. And then you make the finite element space by insisting that if two simplices have a common face, the degrees of freedom associated to that face are equal. That's the pasting condition. And you have to do that and get commuting projections, and it's quite tricky. But for the de Rham complex in 3D, it had all been completely worked out by work went from the 70s, the 80s, and was finished in the 90s for the most part. And then some of the cubes were even discovered later. And when we looked at it from the exterior calculus point of view, we saw how to do it in a completely systematic way for the de Rham complex in ND. And that led to this. And I kid you not, when I got here, there was a copy of this in my office, and I don't know why, but it was sitting there on my desk. It's very old because the colors have faded out completely. This tells you what the finite elements are, what those three things are, and the information here explains how you select from them to get subcomplexes with bounded cochain projections. Roughly speaking, the top three lines are the one-dimensional elements, then the two-dimensional elements, then the three-dimensional elements, and in principle this could go on forever. The three lines are the linear elements, quadratic elements, cubic elements for each one, and that could go on forever. And going this direction in 3 dimensions, 0 forms, 1 forms, 2 forms, and 3 forms. There are 2 different families, the PR minus lambda k family and the PR lambda k family. And we also worked out what it is in cubes, and some of these actually were missing and had to be discovered to fill in the periodic table. And I still have a few of these left, so if you want one, send me your mailing address, and if I have one, I'll send it. Okay, so that's a quick review of the highlights of finite element exterior calculus. Now let's talk about Einstein-Bianchi. So a quick review of curvature tensors. If you're on a pseudo-Riemannian manifold or Riemannian manifold, you have a Riemann tensor. It's a fourth order tensor, Riem or RABCD, which captures all the intrinsic curvature determined by some metric. And there's an easy formula, or a pretty easy formula for the Riemann curvature in terms of the second derivatives and the first derivatives of the metric. It satisfies a bunch of symmetries, so as a fourth order tensor, you might think it has 256 components in 4 dimensions, but actually reduces to 20 because it's antisymmetric in the first 2 variables and antisymmetric in the last 2 indices. For the mathematicians who aren't used to this, the parentheses around the indices means take the symmetric part with respect to those indices. That vanishes, so it's antisymmetric. It's also symmetric with respect to interchanging the pairs of indices, AB with CD, and it's the antisymmetric, total antisymmetric part is 0, so it has an additional symmetry. That reduces it to 20 components. And it satisfies a differential identity too. For any metric, the Riemann tensor satisfies this combination. This is a sum of derivatives. First derivative of the Riemann tensor is equal to 0. That's the famous Bianchi identity. Then the Ricci tensor is the trace of the Riemann tensor. You can't take the trace with the first 2 indices because they're antisymmetric. You get 0. So take the trace with respect to A and C, and you get something with 2 indices, B and D, called the Ricci tensor. That has 10 components. It's a symmetric 4x4 matrix. And the Einstein equations are nothing other than that tensor vanishes. Okay, so Einstein tensors are easy. How many equations can you write down on one slide and explain the whole thing? But getting into the details, it gets more complicated. Then there's the Weyl curvature. What's the Weyl curvature? Well, we have the Riemann tensor and we have its trace as the Ricci tensor. Subtract the Ricci tensor from the Riemann tensor. Well, you can't subtract a second order tensor from a fourth order tensor, but what would you think I meant if I said you have a matrix, subtract a constant? You'd subtract a constant times the identity matrix. The equivalent of that is you encode the Ricci tensor into a fourth order tensor using the metric that's sort of the Ricci embedded in the Riemann, and the difference between the full Riemann and that Ricci part of the Riemann is called the Weyl tensor, CABCD. So in short, Riemann is Ricci plus Weyl. The Weyl tensor satisfies all the symmetries of the Riemann tensor and is also trace-free. And since the Einstein equations are Ricci vanishes, then you can also write them as Riemann equals Weyl. So that's another form of the Einstein tensor equations. Okay, now I go to the Einstein-Bianchi equations following Friedrich in 96 and Anderson, Choquet, Bruhat, and York in 97. What they do is they take the once contracted Bianchi identity, which leads you this third order tensor, div Riem, and these combinations of the gradients of the Ricci tensor. And now if so this always holds, and if the vacuum Einstein equations hold, you can replace this Riem with Weyl, because that is the vacuum Einstein equations. And if the vacuum Einstein equations hold, you can get rid of the Ricci's because they're 0 in the vacuum. So altogether you get that the divergence of Weyl is 0. So this is another way to write the vacuum Einstein equations, or at least it's a implication of the vacuum Einstein equations. And this is the system that Einstein-Bianchi uses to determine Weyl. So what kind of system is this? Well, there's this thing called the Bell decomposition, which sort of gives clarity to the structure of these equations. And I'm going to be a coward. Well, I don't have time to explain Bell's decomposition fully, so I'll drop down to the linearized case here. This is Vincent Kenneville-Bellaire's thesis, and he did the nonlinear case, and Choquet, Bruhat, York, and Anderson, and Friedrichs did the nonlinear case. So we look at CABCD as a 6x6 matrix where the indices for the rows are the pair AB and for the columns are the pair CD. And since they're anti-symmetric, we can always assume A is less than B and C is less than D, so these are the only pairs we have to consider, 6 of them. So then we do a 3 plus 1 decomposition, considering something spatial if its first index is 0 and temporal otherwise. And so we have the time-time components, the time-space components, space-time components, and the space-space components. And then we give them the suggestive names for these 3 by 3 matrices, E, B, H, and D. Sort of funny. We weren't doing electromagnetism, but that's what everybody does. And what is this like? Well, this is fairly similar to taking the true E and B of electromagnetism, which are 3 vectors, and putting them in a big skew-symmetric 4 by 4 matrix. That's the matrix of the Faraday form. Or if you want to think at a little higher level in terms of differential forms, you get a space-time differential 2 form as dt wedge spatial differential 1 form plus a spatial differential 2 form. That's the Faraday decomposition or something. So we do something similar with Weyl, giving us EBHD. Now we have to impose 2 things. The symmetries of the Weyl tensor have to be satisfied, and the divergence of the Weyl tensor has to be equal to 0. Okay, symmetry of the Weyl tensor, any of you could calculate it, just write out what comes out, and you find that it satisfies all those symmetries if and only if H is equal to B, D is equal to minus E, and both E and B are symmetric and trace-free. Those are the symmetries of the Weyl tensor, written in terms of these. And so it reduces to this form, EB, B minus E, where E and B are symmetric trace-free. And we still have to propose the condition divergence equals 0 onto this thing. So what is that? There it is. Divergence of C is 0. We write it in terms of E and B. Well, there are 3 indices here, B, C, and D. We take the values B equals 0, and then B equals 1, B equals 2, B equals 3. And each of those gives us 6 equations for 6 possible pairs C, D. For B equals 0, the equations are divergence E is 0. So this is a 3 by 3 symmetric matrix. Don't let it fool you. It's called E, but it's a 3 by 3 symmetric trace-free matrix. And its divergence has to be 0, and same with B. So it is beginning to look sort of Maxwell-like. And for B is 1, 2, and 3, we get exactly the evolution equations. E dot is minus curl B, B dot is curl E. So this is beautiful. I think I first heard this from George Frauendier, who couldn't come to this workshop. I couldn't believe it. So it looks exactly like Maxwell's equations, but E and B are symmetric trace-free matrices. They are 5 variables each, not 3. And it turns out these constraints propagate. You can almost see that. Well, no, it's not so easy to see that. It turns out that these propagate. You have to show that if you solve this evolution equation and you start with E and B being symmetric, trace-free, and divergence-free, then the solution will be for all time. That comes down to showing that if you have a symmetric, trace-free, divergence-free, or call it TSD, matrix, that its curl by rows is also TSD. It's obvious since it's a curl, it's divergence-free. How do you know that it's symmetric and trace-free? Well, that goes back to something that Ragnar had on his slides, this picture of calculus identities that you get by putting maps between de Rham complexes. So this is the de Rham complex. And then on the bottom I repeated it, and the middle is the de Rham complex tensor vector fields for these two. These are really 0 form valued de Rham complex, 1 form valued de Rham complex, 2 form valued de Rham complex, and 3 form valued de Rham complex. And we have these mappings going up diagonally between them. And one of them tells us that the trace of the curl of a matrix is the divergence of its negative skew part. So if the matrix is symmetric, the trace of the curl is 0. And another one tells us that the skew part of the curl of a matrix is the divergence of S of the matrix, where S is the transpose minus the trace times the identity. If the thing is trace-free, this is gone. If it's symmetric, the identity is gone, and so it's just the divergence of the matrix. And if it's divergence-free, that's gone. So it all hangs together rather nicely. Okay, now what I tell you, and now you should be impressed, Einstein-Bianchi is nothing but a Hodge wave equation for a different complex. So that's what we like. We don't like systems that we can't explain why they work. This one has a structure. So there's the complex. The first operator is not a first-order differential operator. It's a second-order differential operator, a Hessian. And the second operator is the curl, not acting on an arbitrary matrix, but acting on a symmetric matrix and mapping it to a trace-free matrix. Curl always takes symmetric to trace-free, thanks to this, this parallelogram here. Okay, once you have the complex, you write down that complex, you can write out the method. This is the Hodge-Laplacian. We know it's well posed and all that. And we can prove the same theorem we proved for the others. If we start with compatible data with sigma 0, we get a TSD solution with sigma 0 for all time, which means that we solve Einstein-Bianchi equations. Okay, what's the next step? We want to take Galerkin subspaces that form subcomplexes with bounded cochain projections. Then we have the Feec way to solve the Einstein equations. And it's not easy, because second-order operators are much harder to deal with in finite elements than first-order operators. They don't have to be continuous finite elements. They have to be C1 finite elements. And what's more, it's not so easy to deal with the constraints of symmetric and trace-free. And I'm not going to tell you too much except that both of those problems had been solved in other contexts, and they lead to a method. And I'm going to skip over this for lack of time. But the method ends up using 6 spaces. E is here, B is here, sigma is up here, and then these other ones, like for instance, to get the Hessian, we take a pair of functions, a function and a vector field, for which the gradient of the function is equal to the vector field, and then we take the gradient of the vector field to get the Hessian. So it's sort of a little complicated. Franz? Where comes linearized? This Bell decomposition is much more complicated for the full Weyl tensor. This was a linear. This part was linearized.
Well, that you can do in general.
There is a Bell decomposition, but it's much more complicated to write down. It's not just write down a matrix and partition the matrix, because in writing down this matrix, I think I'm sort of using a flat background.
No, you don't have to. It really isn't more complicated.
Really?
But the analog of Maxwell's equations becomes more complicated.
Covariant gradients instead of just flat.
Okay. Well, let's talk about that afterwards. Well, that's what we do. So we take two variables. The one we want to take the Hessian on is living over here, but we only take its gradient, but we have an equation that says there's another function that's going to be equal to that gradient, and in the numerical method approximately equal to the gradient, and we take the gradient of that. So this is breaking grad into grad and grad on 2 functions. It's that method. But the point is, you can't just take any numerical method and introduce new variables and always expect it to work. It's something worth trying, but then you have to ask whether it works. And if you can keep it sort of as a... So we have some tools to say that this method will work for that kind of Hodge-Laplacian. And then we got to the point of, so my student finished this stuff, and I said, okay, now you have to do some computation so people believe it really works. And that's when he graduated and took a job in big data. And the only thing I managed to get out of him, I insisted on something. He took a plane wave and translated over a linearized background, and it worked perfectly well. But I don't have impressive computations. Okay, any questions? Okay, the second thing I want to talk is about a little bit of observations of Reggie calculus, and I had the advantage of Warner speaking before me. This is much more in the line of some observations and some questions rather than a proposed method. This was a PhD student of thesis of my student Li Tsao Li, and he's working for BlackRock Financial, so I don't know what I'm doing wrong. Okay, so the question I'm going to ask is the following. You want to solve a PDE for which the unknown is a metric. I think there's a lot of people here who want to do that. What kind of finite elements should we use for metrics? We found out that if you have a differential form, you should use a special kind of finite element for that degree differential form. What should we use for a metric? That's not a differential form. Okay, Well, for any question you cannot answer, there's an easier question you cannot answer. And in this case, there's an easier question we can answer, which is what do you use for just zero forms, for regular functions? If we want to take functions in the domain of the gradient in the space H1, what finite elements should we use? Everybody knows the answer. It was determined back in the 60s. Use the Lagrange finite elements that Ragnar presented. Piecewise polynomials of degree R with degrees of freedom set up to enforce continuity. So how do you do it according to our definition of finite elements? Well, the shape is a simplex, triangle in 2D, tet in 3D, hypersimplex in 4D, and so forth. The shape functions are polynomials of degree R or less on the simplex. So here I do the picture of cubics on a 3-dimensional simplex. That's a 20-dimensional space. And then you give the degrees of freedom, and for the Lagrange elements, it's the traces of the function, the restrictions to the boundary, to the face, weighted against a weighting function, taking a moment of degree, and the degree of the moment gets lower and lower as you get to a higher dimensional face. So we have the functions at the vertices, then moments of degree R minus 2 on the edges, and then moments of degree R minus 3 on the faces, and so forth. And you can prove in general in n dimensions for all R that these degrees of freedom are correct in number, and you'll get the set of all continuous piecewise PR functions. So this is the goal, something as clean and as nice as that. So how do we do it for differential forms? Well, that's what Ragnar talked about. We have 2 answers to that question, the PR minus spaces. And to define them, you have to get into the Kazul operator, and it's a little fancy. And to give their degrees of freedom, you use PR spaces without the minus. And that's always unisolvent, and that always works. And the other answer is to use the PR spaces, and for the degrees of freedom, use the PR minus spaces. Okay, so we have a lot of models of what we'd like to accomplish. So what are the canonical finite element spaces for metrics? Symmetric, not skew-symmetric, covariant tensors of rank 2. And so the claim is that they're very related to Reggie's idea, the Reggie calculus. So we've heard a lot that Reggie developed a discrete analog of GR where space-time was a simplicial complex, and the metric is the assignment of the length squared to each edge. Take squared so you can assign negative length for pseudo-Riemannian metrics. Then the curvature is in the n-2 skeleton, which Sonora and Warner called hinges and I call bones, and it's measured by the dihedral angle deficits. And the Hilbert action is the sum of over the bones of the angle deficit on the bone times the volume of the bone. We don't need to introduce the dual mesh in our view of this. And you could think of that as integrating density, which is a singular density. It's concentrated on the bones, which is a discrete curvature density. And the Cheeger-Muller-Schroeder famous result is that this thing converges to the true curvature density in the sense of measures. Okay, now I claim that that can be viewed as sort of a finite element interpolation. So I give the 3 things. The element shape is a simplex. The shape functions on every simplex, I give constant symmetric n by n matrices, or constant metrics to be more accurate. But if we have a coordinate system, constant symmetric n by n matrices. And the degrees of freedom are the lengths of the edges, or the length squares of the edges. That's in, say, 2D, a 2 by 2 symmetric matrix has 3 variables, and we have 3 edges, and so they're the right number, and you can prove that they're unisolvent. In 3D, a 3 by 3 symmetric matrix has 6 variables, there are 6 edges, and you can prove it's unisolvent. And of course, you can do it in ND. Then what happens if you use these degrees of freedom to patch together a space? You get piecewise constant metrics, but not all piecewise constant metrics. They have a well-defined tangential component, which means that if the common face of 2 simplices, vectors lying in that face are measured the same from the left and the right. So that's a finite element space. So I'm very appreciative of what Warner said, that Reggie calculus looks like DEC applied to relativity, but it also looks like a very low order kind of Feec applied to relativity. And in fact, Feec looks like a very low order kind of, DEC looks like a very low order kind of Feec in general in some sense. Okay, what could you do with this? Well, had to do something, and Larry's actually a good programmer. And here's something that falls way short of solving any equations. He did the following thing. He said, suppose you have a metric, and you interpolate it into the Reggie metric. So you find the piecewise constant metric that gives the same edge lengths as the true metric. Then you have a coarse approximation. Well, how coarse it is depends on how fine your triangulation is. You have an approximation of some metric. Then you could compute the geodesics in the interpolated metric, and maybe that'd be a good approximation for the geodesics in the true metric. And the test case I have up here is I took the Jacobi metric for the Kepler problem. This is some non-flat metric whose geodesics are Kepler orbits, ellipses. So this geodesic, it's actually moving straight across each element because there's a constant metric, and making a turn to preserve the normal component, a sort of Snell's law, because the tangential component is continuous, but the normal is not. I won't get into that, but this is the right way to compute a geodesic in Reggie. And if this was a very good method, this would be a single ellipse. And the fact that it's missing is showing that this is a coarse approximation. And why is it a coarse approximation? Because we're using piecewise constants. What did you expect? Okay, so then we moved on to the question, well, nobody uses piecewise constant. Even piecewise linear finite elements are getting sort of old. People are now using cubics, quintics, 10th degree polynomials very often. Is there Reggie elements of higher degree? And that's the main contribution of Larry's thesis. The full family of Reggie elements, sort of a finite element, a periodic table of finite elements for metrics, would have a new column for metrics. The element shape is simplices. The shape functions are polynomial of degree r metrics, instead of constant metrics on each piece. And then what are the degrees of freedom? That's the only thing that's hard to choose. And it's a little fancy. If you go to a face of dimension d, you look at all the edges that face has. For each of those edges, you compute its edge length with the metric. The metric is variable over the face, so you compute the average, the integral of the edge over the face, weighted by polynomials of degree r minus d minus 1. So for example, in this case, this is the case of linear rather than constant Reggie metrics on a triangle. You take the length of the triangle and the first moment of the length of the triangle computed using the metric along the edge, which is variable, to get 2 degrees of freedom. You do that in the 3 edges to get 6 degrees of freedom. And then in the interior of the triangle, for each of the 3 edges, you use only its constant moment. You're giving 3 more. Those are 9 things, which are how many you need for a metric which is varying as a linear polynomial in 2 dimensions. And you can do something similar with higher degree. And you can do something in different number of dimensions. The middle row is what you just saw, but there's 1 dimension and there's 3 dimensions, and you can do it in n dimensions. So for example, we could have done this calculation. Instead of using piecewise constants, we can use piecewise cubics, and that's what we did, and you get that. So now we've computed by solving the geodesic equation. We move across the triangle, then we do the Snell's law, and we get a very nice metric. That's 50 orbits there. How do we compute the geodesics? So here's what I'm doing. I have a piece of space with a metric on it. That means at every point x, I have a symmetric 2 by 2 matrix, right? That I use to measure the lengths. Lengths are the length of a vector t would be t transpose g of xt. And then you'd integrate that over a path to get a length, right? Okay, what I do is I put a triangulation, any triangulation I want, well, you see the triangulation there, over the thing, and then I figure out the length of these edges and the first moments of the length and the second moments. Those are what I need to interpolate by a cubic. So I get a new metric, GH, which on each triangle is a cubic polynomial. Okay, so now I have a piecewise cubic metric. Okay, now let's just look at 2 triangles and compute a geodesic. It comes in with a certain velocity vector here. I solve the geodesic equation in this cubic metric, which gets me some sort of curve, till it hits another edge. And let me not hit it at a normal angle. Now I have to jump over to here and continue. But the tangent vector here has a tangential part and a normal part. And you have to be careful because there's a different metric here and here, so there's two different normals. There's the normal n plus and a normal, let's make it pointing the same direction, n minus, but they're not collinear because I have a different metric here than here. The metric's not continuous, only its tangential part is continuous. So because I want to conserve energy, the tangential part will stay the same because that is continuous, and the normal part has to have the same magnitude. So if the thing was alpha n minus plus t going in, I'd do alpha n plus t going out, where this is n plus and this is n minus. So that's what I do. I solve the geodesic equation to get here. I break it down as alpha n minus plus t. I change n minus to n plus, which turns this thing a little bit. And I do the geodesic again, and so forth. That's what I'm doing here.
Polynomials, why isn't the normal direction continuous?
Because Reggie metrics only enforce continuity, the tangential component.
Very lowest order, but I would have thought that if you went to cubic order, you would have also got the normal direction.
If you want to know what's continuous, is on a face of dimension f, the metric is continuous only its moments of degree r minus d plus 1. You don't have enough degrees of freedom in a cubic to end up with a completely continuous metric. Well, I could insist on having a completely continuous metric, but they wouldn't have the good properties that you need for stability and so forth. So this is getting to the question, what are the right kind of finite elements for metrics? And in some sense, I think tangential, continuous, piecewise polynomials have many things to say for them.
Yeah, I mean, that's fine. I mean, basically, you're putting in some, like, Israel tails on the edges of your
That's, you say so.
well, I mean,
There's going to be discontinuities and extrinsic curvatures across the faces. What do you say?
yeah, I mean, you're required to have the tangential metric be continuous for consistency with Einstein's equation, but as a distribution.
I mean, it's sort of like for H1 finite elements, we use Lagrange elements, and then we have trouble if we try to compute Hessians. You have to do something clever, because they're not so great for Hessians, but they're really great for H1. And these are, well, they're probably the least continuous thing for which you can still compute curvatures and so forth. Warner.
Back in the piecewise flat example where things didn't match up very well, if you were to take the particle and spread it out over multiple cells and define your geodesic as an average over what they're doing, then they're going to go on either side of the singularity and they're going to get some type of convergence. Would that be a,
You might be able to do so.
is that equivalent? Would that be
Well, the fact of the matter, if you take a metric and you approximate it by piecewise constant metrics, the error is going to be order of h, where h is the size of the element. That's the way life is. So if h is not very small, it's not going to be very accurate.
But if you take the particle and smear it out
Then you'll get something that is smoother, but not more accurate.
to the right and they cancel, do you get a next higher order?
I doubt it. I mean, it's not, I doubt it, but I mean, maybe there's ways to do it. This is sort of a cooked up problem. What's that? So this is a piece of pure math called Jacobi metric. So there, if you have a manifold, there's a metric whose geodesics are the Jacobi orbits. And actually, there's something that was invented by Gary Gibbon here in Cambridge, which I'll show you now. He found the Jacobi metric for Schwarzschild black holes, in the sense that there's a metric which you can't see, but it's somehow represented on this mesh. This is the piecewise constant interpolation of that metric, whose geodesics are orbits around a Schwarzschild black hole. And this is supposed to look a little ugly because we expect orbit around a Schwarzschild black hole to be precessing in a uniform way, and this is not. That's with piecewise constant Reggie elements, and this is with piecewise cubic Reggie elements. You get this nice, beautiful, symmetric thing. But this is still somewhat a cooked up problem. I don't think most people wake up in the morning saying, how could I interpolate my metric so I can compute geodesics on it? But if you did, this would be a way to go. Okay, and finally, this is an important observation, the last thing I want to say. This, I think, well, this makes you think about Reggie calculus, makes me think hard about it, and I'm not quite sure what the conclusions are. So as Warner said again, Sorkin was the one who turned Reggie calculus into a numerical method where you could march forward in time, 10 pitching or something like that, and solve the Einstein equations in something like a real usable numerical method. This was he published his thesis in '75 in 2 papers, and he had this nice statement that full-blown computer calculations ought to be possible, but my own attempts succeeded only in developing programs that calculate the basic quantities, but not in solving efficiently the equations for time evolution. Of course, who can blame him? It was 1975. But then he had a very interesting idea, which is very much in the spirit of a mathematician. He said, well, I can't implement this, so let me go to some easier model problem and see if it works there. And what's the easiest model problem? Well, the wave equation is the easiest model problem for a hyperbolic. So he said, do the following. Take your action to be this, and ask for that action to be stationary. That gives you the wave equation. In fact, if there was a plus sign there, this would be the way that you solve the Laplacian by finite elements that Ragnar wrote down on his first slide. But now there's a minus sign, so you get the wave equation. And he said, apply this to a simple problem. I think this is exactly the problem he did. The initial value problem with Neumann boundary conditions on a rectangle. And he just did it in 2D. And he said, what's the Reggie way to do that? Well, I'd restrict these to the simplest possible piecewise polynomials, which would be piecewise linears for this problem, not piecewise constants. You can't make sense of that with piecewise constants. So he discretized with this mesh, the simplest of all possible meshes, and he used continuous piecewise linear Lagrange finite elements. He didn't quite think in terms of finite elements because he said something that there's a new method out there called finite elements that this seems to have something to do with. But it was brand new at the moment. And he worked it out by hand, and he said, well, the equations are the leapfrog method. This is the equations that you get out of this, exactly the leapfrog method. And then he drew his conclusion. He said, well, the leapfrog method is known to be convergent as long as you satisfy CFL condition. So this gives us great hope that when we tried the simplest problem, we recovered a well-known method that works. And this is more or less how he marches. You start off from your initial data generating 2 time levels of values. You know the boundary values. And then you take a test function centered at that red dot, and that allows you to push forward to the blue dot, which is the only unknown in the equation. Then you slide that down one and get the next blue dot and so forth, and you can march forward in time. Okay, and if you try that, you get this. And this is a pretty boring thing because what I'm showing you the leapfrog method. You've probably done this in one of your undergraduate classes. It works. I am well within the CFL condition, nothing goes wrong. But then we did the following thing. Instead of taking this mesh, we took a small perturbation of this mesh. And Litzau Li eventually found a devilishly clever small perturbation. What he does is he doesn't change the initial values. He doesn't change the boundary value points. He moves certain interior points upward in a purely spatial direction. So he doesn't change the temporal slices. They're still in slice, but this moves up 5%. And he does that not every one and not every second one, but every third one moves up 5%. You get a slightly different mesh. Here's a blow up of it. You can hardly see the difference. And this is what happens when you compute with that. Looks pretty good till about now.
Is that because the first one is symmetric and the other one is not?
I don't know. I'm in the right. Good question. I'm in the right place to ask that question. But actually, so because Larry picked this one where you do it, every third one you do it exactly in a systematic way, you can actually do von Neumann stability analysis for this. This is unstable in a von Neumann sense. So I don't think symplecticity is really the right thing. But it's unstable in a von Neumann sense, but I don't think there's any CFL violation. We're way within the CFL condition. 1 second, Luis, I'll get you. Let me just put on this thing. Here are 4 cases. Here instead I'm plotting versus time the L2 norm of the solution. And this is the uniform mesh, and it's just periodic. And it seems it'll go on forever. This is the one that you just saw. You notice I've changed the scale, so it's just periodic between 1 and 1.5 for quite a while. But then when we got out to time 50, you saw it blow up exponentially. This is the same thing with a 1% mesh perturbation. It goes 5 times as long, but then it blows up exponentially just the same. And this one, instead of this devilishly clever perturbation, is a random perturbation of all the interior mesh points of 10%, and this one also blows up. So I'll give so what's the moral of this story? Well, it seems to me if Reggie calculus, that was supposed to be a sort of a very general thing. You're supposed to be able to put down any mesh and handle nonlinearities and so forth. And it seems to me as a straight method, well, I don't know about for Einstein, but for solving the wave equation in this analog of Sorkin's, if you think it's a real analog, you could argue with that too. This analog of Sorkin's, I think this is actually warning us that it's not a good method, not that it is a good method. And what do we take away from that? Well, I think what's going wrong here? What's going wrong is we're solving a 1 + 1 problem, time and space, as if it were a 2 problem, a 0 + 2 problem, as if we were using the Laplacian. We're using the same finite element method we use for the Laplacian, just putting a minus sign in front of one term. Everybody knows you can't solve elliptic problems and hyperbolic problems with the same method. So what to do about it? I would think that maybe the place to explore Reggie would be to use 3-dimensional Reggie to approximate the spatial curvatures in operators and a more standard time stepping for the time space, maybe something symplectic. But now I'm being totally speculative, and I throw the floor open.
I wonder in that example whether this is happening with the boundary. Because we try just wrapping around and going periodic, no boundaries.
I think we did periodic, but I'm not positive. I should check it.
And the other one can please try and what you just said.
Sure.
You cannot use the same time as you could in the space. So let me line the following again. What's the advection equation? It's going that way, so it's up around. I can use the Hooker going to interior this way. I can use the Hooker to interior that way. So what would you say?
I didn't say you couldn't use the same methods for space and time. You can't use the same methods for hyperbolic and elliptic. So, I mean, do the following method. Use the method that is the #1 method for solving elliptic equations, piecewise linear finite elements, or centered finite differences you want, 5.5 finite differences, and try to solve the advection equation with them. Right? You centered finite differences for the advection equation doesn't work, right? It's not stable. So in some sense, the character of hyperbolicity and ellipticity is extremely important. You can write them so they both look like the Laplacian because you have a metric with a funny signature, but you didn't change their fundamental character.
You had said that the method of approximating metrics was similar to the angle deficit. How do you make
No. So that metric stuff didn't have anything to say about the Reggie way of computing curvature. Just, I mean, it was fairly obvious it would work in a sense, but.
I have a question about the geodesic example. Do you know the convergence rate against the actual geodesics?
That's a good question. It's probably in the thesis. I mean, I'm sure it's. Okay, so the question is,
Is it the order of the elements?
Yes, I'm not sure whether it's +1 or equal to, but it'll certainly go up with the order of the elements. And we have the calculations for constants, linears, quadratics, cubics. I just showed you the cubics, which are perfect to the eye on that mesh.
It should be the order of the elements plus or minus 1%.
I mean, you're asking the following question. Suppose the geodesic equation looks like y double dot equals some Christoffel symbols squared of y. So if you change the Christoffel symbols by changing the metric, which is, yeah, it must be the degree of the metric. So the metric is approximated by a cubic, which means it's fourth order accurate in the metric values and third order accurate in the derivatives of the metric values. It's the derivatives that go into the geodesic equation. So what you've done is you've changed the coefficient of the ODE to order h cubed. So you're going to change the solution to order h cubed. I'm pretty sure that's the way it would work out.
So you are solving an ODE across the face where the left-hand side and the right-hand side are different, right? I mean, the right-hand side of the ODE on this side of the face and that side of the face is different. The constants, the coefficients are different. The right-hand side is different, right? The geodesic equation on
Yes, because they have Christoffel symbols of the metric in the equation, and the metric is not continuous.
So now, if you have a ODE method which doesn't sort of carefully track when it's crossing over in a discontinuous right-hand side system, then you can destroy the order of.
And here's the example to prove that. Let's take the lowest order case of constant metrics. Well, when you go across, the geodesics are straight lines because of constant metric. You don't do anything at the thing. You just go, all the geodesics would just be straight lines. Right? In the lowest order case, the metrics are polygonal, piecewise straight lines, and the only turning they do is when they cross from one element into another. So if you don't do that, you wouldn't do anything. Okay?
So the ODE integrator doesn't have to be messed around.
Well, we use a symplectic. I'm glad to say we use a symplectic ODE integrator to do the geodesic equations across each element. Then you had to do some sort of detection when you hit the edge of the element. Then do this little Snell's law rotation and then pick up again. That leads to some issues, and Larry solved them, but they're small.
So David and then David.
A comment about using the electric and magnetic parts as a toy model for GR. I think that there's something really is lacking in that as a toy model, because in the case of, say, limited electromagnetism, it's perfectly consistent with just evolving in here and chuck away the vector potential. But in GR, we will always have to evolve the metric. Right? Like, there's no way to get rid of that thing. So I think it would be very good and important to append to that model also the metric and first derivatives of the metric in an appropriate way. So the question is, if you do that, can you also write that down in the form that you need, or in the form that you like, rather?
I
Do you know if that's true?
don't know if it's true. Think I know pretty much what you're talking about, but I'm not sure I know the solution. Is this really already the same problem that arises with the wave equation? If you remember, my variables were the velocity and the d and the d star, but the original variable, capital U, wasn't a variable anymore. So I should have appended capital U dot equals little u. That's like that, right?
Well, except it's worse.
But it's,
because the
yeah.
derivatives are really the covariant derivatives, and you need the metric to get that connection. So you can't even write the whole equation.
I told you it was easier in the linearized case. Yeah. No, so, I mean, what's the real story here? This is a toy problem, and there's no way that us being able to solve this will convince you that we can solve Einstein or convince me or anybody else. On the other hand, the question is, does this illuminate at all the situation, or is this so trivial that it's...
I don't have any objection to the use of that as a model, but I'm just saying that I think it will be important to append also other variables to that system,
You're
which
suggesting
isn't
your
the
second.
case. If you're
Yeah.
just worried about Maxwell,
It's one toy among many that are needed. And as yesterday I said, I mean, we need the model where you propagate exactly nonlinear constraints. We need a toy with that property. I mean, this is very far from that one as well. No, I agree with you, and I would be happy to talk a little more about what way this could go, especially if somebody wants to pick up this research.
so one of the examples that you gave was the flat space-time wave equation. Do you have a way of generalizing your method so that you could also do the curved space-time wave equation? I mean, I hand you some metric, and you want to solve, del
Yeah, sure. So, I mean, just like we can solve the Laplacian, finite elements can solve the Laplace-Beltrami operator with no more problem. It's just so. Now I got myself in trouble. I don't know if I can write down Laplace-Beltrami, but there's certainly a ddxi of gij ddxj. Got to put a 1 over g somewhere. Anybody know? Anyway, so let's say there was a 1 over g here. You'd multiply this equation by g. You'd multiply it by a test function. You'd integrate this by parts. And now you just have a weighted by g inner product, and everything else is the same.
But you have an inverse metric sitting in there as well.
Yeah, so you put the inverse metric in there.
But that's okay.
Yeah, that's okay.
Okay.
I mean, so one thing finite elements doesn't have a problem with. So we do the Laplacian all the time, but we know in our heads that you could add variable coefficients, and in fact you could add mild nonlinearities if they don't change the fundamental character of the problem. That's not, I mean, it's not that hard to solve g of u grad u grad v equals fv. That's a semi-linear problem or a quasi-linear problem. Of course, if g of u doesn't have nice properties, maybe there's not unique solutions or something like that. We don't address that. But if this has locally unique solutions, you can calculate those with finite elements. And the issues that arise are already taken care of in the Laplacian case, which is why we talk about that case.
Well, I mean, so in that case, you might be closer to solving Einstein's equation than you think, because this is not, necessarily, elegant and geometrical, but I mean, in harmonic coordinates, Einstein's equation looks a lot like, the wave equation for the metric components, and on a curved metric, and so, with sort of lower order nonlinearities. So if you can solve the curved space-time wave equation, you may very well be able to solve Einstein's equation in harmonic coordinates.
Well, this was sort of, right, this was what Franz's revelation was, that you go into the harmonic coordinates and it's like a coupled set of nonlinear wave equations, and a lot of different codes could be used to try to solve that problem. And I agree with you, finite elements could be used for that. No, but for numerical purposes.
No, but I mean, a couple of decades before Franz, Yvonne tried to talk numerical people into using harmonic coordinates, and they wouldn't do it.
She didn't call me.
I'm vaguely aware that people who have thought PDEs and using the space-time DG methods. Do you have a sense of why those don't run into trouble, whereas this sort of Lagrange finite element method did?
Well, space-time DG methods are really an attempt, a successful attempt in many cases, to handle space and time in a different way. They're sort of DG in time, more or less. They tend to line up the so for example, not from the meshes, I don't think. I mean, maybe I'm not caught up to these things. Actually, so one of the early space-time DG people was Rick Falk and Jerry Richter. You published both CG and DG methods for solving hyperbolic problems. And the main thing was, it was important that the triangulations be aligned somewhat with the right causality. I mean, you can't get away from causality, right? That's the reason that you have to treat the evolution differently. You have to obey domains of dependence and so forth. And I think these methods don't put it on the same footing, really. In the same how the jumps in the DG line up with the characteristics.